All right. So guys, if we could flick to the integral calculus page, so SAT 4 for integration. So we'll do a recap of this, and then you've got the 2 tests there that you can dedicate your efforts towards for the remainder of the learning time. All right, so for SAT 4, we went through 4A and 4B were mostly area under the curve. 4B introduces to the idea of backwards differentiation. And you might remember when we did this chapter, we went from 4A and then we sort of skipped ahead to 4D and E when we started talking about rules of integration. And then we sort of did the chapter in a bit of a different way than it's presented. So chapter 4 was mostly rules for integration. So what we're going to recap over the page then is how to perform these integrals. So the first one that we have here is the integral of 6x squared plus 5x take away 7 with regards to x. It's an indefinite integral because it doesn't have a boundary. So all we're required to do is find the antiderivative. All right, so just like calculus, like differential calculus, we integrate term by term. And so what we have here, like I might break it up, I think we can do this really easily, but I just want to make sure we're all clear. This is the kind of thing we're doing, right? We're integrating that one, we're integrating this one, 5 lots of the integral of x, and then we have the integral of 7. All right, so that's what's going on. We're integrating all of those. Now we know x squared goes to x to the 3 on top of 3. 5x is 5x squared on top of 2. And 7 goes to 7x. And because it's an indefinite integral, we need our plus c. Very good. And we can simplify a little bit here. You can put that as 2.5 if you wanted, but it's all fine. Okay, on to b. We have e to the 4x plus 3. Now the rule for e is if we have e to the kx, or ax plus b, it goes to 1 on a, e to the ax plus b. So in this circumstance, when we integrate it, we'll have 1 on 4, e to the 4x plus 3, plus c. All right, on to c. We have the integral of 5x take 4 to the power of 3. So here we have ax plus b to the power of n. The ruler. Alright, so that's the rule. So here we're going to have 1 on 5, and then we'll have 5x take 4 to the power of 4 on top of 4, and then plus c. And we could simplify that a little bit. The denominator will be 20, but otherwise that's fine. All right, and then for D, D is another application of this rule. It's just a little bit more complex. We have the integral of 8 on top of the cubed root of 7x plus 2. So the first thing we want to do is express it in a manner ready to integrate. So we would write it as 8 times 7x plus 2 to the power of negative the third. And then we're going to have, the 8's going to hang out the front, and we're going to have 1 on a, ax plus b to the power of n plus 1 on top of n plus 1, and then plus c. All right, and we could simplify that. It's going to become 3/8, 24 on 14, 7x plus 2 to the power of 2 on 3. Very good, so that's A, B, C, D. Let's move on to number 2. We have evaluate here, we've got a definite integral this time. We have the integral from 0 to pi on 2 of cos of x on 2. Now, remember, anytime we have x on top of 2 or on top of a number, we should always think about it as half times by x. Okay, because now it's like cos of kx or cos of ax. And the integral of cos of ax plus b is negative 1 on a sine of ax plus b. So in this circumstance, we're going to integrate to our square brackets. We're going to have negative 1 on top of a half will simplify to -2. Sine,
Isn't it?
positive. Integral of cos. When you differentiate sine, it goes to cos. When you differentiate cos, yeah, positive.
Yeah.
Thank you. Sine of half x. Now we don't need plus c this time because we have a boundary. The c's would cancel, and we have from 0 to pi on 2. And so we'll just process here. This becomes 2 sine of half times pi on 2. Take away 2 sine of half times 0. So that component is 0. Now, just because you're subbing 0 in doesn't mean it will automatically go to 0. Okay, you need to be careful. Sine of 0 will be 0, but cos of 0 would be 1. So always be careful. Just because we sub 0 in doesn't mean it goes to 0. And this here becomes sine of pi on 4. Look at the unit circle. Sine of pi on 4 is root 2 on 2. So this will simplify to be root 2. All right, and we've got all of the steps there that we need. We've got the integral statement, we've got the antiderivative with the boundaries, we've performed the substitution, and then we've got the answer. Okay, so that's number 2, and then we'll move on to number 3. Using 2 rectangles, find an upper estimate for the area under the curve of y equals x squared. All right, so here we have the integral from 0 to 2 of x squared. All right, let's sketch it. That's what the function looks like. Here's 2. That's going to be y is 4. Here's 1. That's going to be y is 1. And we've got 2 rectangles to approximate the area. There's the first rectangle. There's the second rectangle. And so for part A, to find the approximate area, this first rectangle has got an area of 1, and this second rectangle has an area of 4, 1 times 4. And so the over estimate is going to be 1 plus 4 over s times 8 is 1 plus 4. Units squared because it's area. Very good. All right, part B, calculate the exact area using technology. So it's just the integral from 0 to 2 of x squared with regards to x. So what's that, x to the 3 on 3, 8 on 3. And then part C, will the upper estimate or the lower estimate be closer? So this popped up in our wine glass folio, it's popped up in the 2018 exam. Because the function is concave up, we can see the curve is closer to the lower end, so the lower estimate would be a better approximation. All right?
Which part is this?
Part C. With B, C. Now, one thing they really like to ask in exams is they really love making a link between differentiation and integration, where you've performed some derivative and then hence you have to integrate. So I think I'll add one of those into here. We could go over one quickly if you want. Yep. So it might be something like, I'll show you where they pop up in the textbook. We can find one in the 2018 probably.
There is one in 2018.
There you go. Should we do it? Yeah. What is it? Differentiate.
Yeah, I think so.
I've got a brand new version of the exam if you like.
Blank coffee. Free blank coffee.
This is where we're playing
As many as you want. You have to do them. Good.
Anything part 2?
What am I looking for?
Yeah, it's question 10.
Question 10. Oh, question 10.
Oh, you're welcome.
All right.
That way, is it? Yeah.
Show that g dash of x is this, and then where
Oh, wait, no, it's not a question.
You might need to use it in the integral statement. Determinant dash dash, ln. I might pull one out the textbook if we can. We'll do a video. So it's chapter 4, and it's on page 118. So it's like question 8, 9, 10, and 11. These all use the same kind of technique. So let's do 10. You've seen this one. Even we can do 10 or we can do 11. Let's do 10. 10 popped up in the textbook in the previous test a fair bit, where it says find d on dx of x cos x, and then hence integrate x sin x. All right. So in exams, they won't be very explicit. Okay, so remember, you never do anything in vain. You never do anything for the sake of no reason. If you perform the differentiation, it's probably going to pop up later. Okay? So if we're going to differentiate this, we're going to use the product rule. All right, so when we differentiate it, we would have u dash v, so it'd be cos of x, plus u v dash x sin x. All right, that if we differentiate this, this is what we obtain. And so the link we have to draw is an integral statement. Because the derivative of this is this part, therefore the integral of this, okay, the integral of cos x, plus x sin x is equal to x cos x. Okay, that's what we're drawing out from the differentiation. And we are asked specifically, what is the integral of x sin x? So this is where we start to use properties of integrals, where we'll split this integral statement here. Okay, and then this just becomes a variable that we can move over to the other side of the equation. We subtract the integral of cos x from both sides. And then we can perform it. Integral of cos x is sin x. Plus.
When you differentiate cos x, it's going negative.
Here.
Up, like up the top.
Yes, that's going to screw things up. Derivative of cos is negative sin u dash v plus u v dash, good job. Alright, so that's a negative there, so that's a negative there. So then we can just shove the negative over the other side. Okay, so that's a good example of differentiation to hence integration. All right, so I'll stop there. We've handed out the test for number 4.